Neutrino mass wasn't supposed to be this small. It may be hinting at hidden dimensions. In the previous parts of this series, we saw how the Pati-Salam model can evade the monopole constraint through the sign of a single parameter. We also explored how artificial intelligence is now helping physicists search for those elusive monopoles. But today's question goes even deeper. Why is the neutrino so light? Popular science often says, open quote, neutrinos are extremely light particles. Their mass is almost zero. Close quote. Real physics says something much more interesting. That almost zero value is one of the biggest mysteries that the standard model cannot explain. Every other known fermion obtains its mass through the combination of a Yukawa coupling and the Higgs mechanism. If neutrinos followed the same pattern, their masses should be at least comparable to the electron mass. But they are not. The 2024 KATRIN experiment established the most stringent direct limit so far. Genu math block widget always prefetch mu 0.45, matharm EV less than 0.45 evols. The difference is more than a millionfold. Physicists therefore proposed a remarkable mechanism to explain this hierarchy. Its name is the seesaw mechanism. Why the seesaw mechanism is so elegant? Proposed independently in 1979 by several groups including Minkli, Yanagida, and Gelman, Ramond, and Slansky, the central idea is astonishingly simple. Genu math block widget always prefetch approx frac MD2 MR extra weak scale 100 GeV. MR equals right-handed neutrino mass, extremely large 1010 squared GeVs. This immediately gives M9 to 100 G squared is play 10 to the G no 0.1 EVs. The small neutrino mass is therefore not produced by a tiny parameter. It emerges naturally from a very large scale sitting in the denominator. Like a playground seesaw, the heavier one side becomes, the lighter the other side appears. Why Pati-Salam makes the seesaw natural? Recall the Pati-Salam symmetry. GPS equals SUL, SU2R, SU4C. In this framework, the right-handed neutrino is not an optional addition. It is required by the symmetry itself. In the standard model, a right-handed neutrino must be inserted by hand. In Pati-Salam, it appears automatically because of the SUR structure. Even more importantly, the mass of the right-handed neutrino is connected to the breaking scale of SU2R. That scale naturally lies around 10^-1 for GeVs. As a result, the seesaw mechanism emerges almost automatically. No extreme fine-tuning is required. The symmetry breaking itself generates the correct scale. Then hidden dimensions enter the story. In 1998, Nima Arkani Hamid, Savas Dimopoulos, and Gia Dvali asked a radical question. What if the right-handed neutrino could move through extra-spatial dimensions? According to the ADD framework, standard model particles are confined to a four-dimensional brane. The right-handed neutrino is different. Because it carries no standard model gauge charge, it may be free to propagate into hidden dimensions. If that happens, a tower of Kaluza-Klein states appears. For every compactification radius r, there exists an infinite collection of heavier neutrino copies. These extra states suppress the effective Yukawa coupling. The remarkable consequence is that an enormous mass scale MR is no longer necessary. Instead, the small neutrino mass can arise from the geometry of extra dimensions themselves. Deans, Dudas, and Gergetta showed that. Genu math block widget always prefetch mu sim frac and m equals fundamental scale. R equals compactification radius. In this picture, neutrino masses become a probe of hidden geometry. The twist, neutrinos could reveal extra dimensions. If neutrino masses originate from this mechanism, neutrino oscillation experiments should carry the fingerprints of extra dimensions. The Kaluza-Klein tower would subtly distort the standard 3-neutrino oscillation pattern. Future experiments may be able to detect these deviations. The upcoming Dune experiment is expected to reach unprecedented sensitivity to such effects during the coming decade. Cosmology also contributes important constraints. Recent DESI results place a strong upper limit on the sum of neutrino masses. Had N0 0.072 EVs, 95% confidence level. Some traditional seesaw scenarios are already under pressure from these limits. Certain extra-dimensional models, however, remain fully compatible. A philosophical ending. The neutrino is the quietest known particle. Roughly 65 billion neutrinos pass through every square centimeter of your body every second. Almost none interact. Almost none leave a trace. Yet perhaps that silence carries a message. Maybe hidden dimensions exist. Maybe we cannot see them directly. But neutrinos may already be traveling through them. And if the mathematics is right, the next generation of experiments may finally reveal where those dimensions are hiding. References: KATRIN collaboration. Direct neutrino mass measurement with subelectron volt sensitivity. Physical Review Letters 133, 251801, 2024. Arkani Hamed, Dimopoulos, Dvali, and March Russell, Neutrino Masses from Large Extra Dimensions, Physical Review D65, 024032, 2001. Dyens, Dudas, and Gergetta, Light Neutrinos Without Heavy Mass Scales, 1998. DESI collaboration, DESI 2024 results, Baryon Acoustic Oscillations, Pati-Salam, Lepton number as the fourth color, Physical Review D10, 275, 1974.